So that looked fine with H2S, but overlapping standard half-filled atomic orbitals doesn't work for most things, turns out. So let's look at carbon and hydrogen. So here we have carbon. It has two half-filled orbitals here, and here's hydrogen with a half-filled orbital. And so we could see this half-filled orbital overlapping with that one, and maybe another hydrogen. It's a particularly obnoxious tree. Same to you, buddy. Yeah, it does. So these orbitals can overlap with each other. So that's what this picture is. Here's the s orbital for carbon, which has a pair of electrons in it. And we have a p orbital that's half-filled and another p orbital that's half-filled. We're not showing this one because it's empty.
Okay.
This one's overlapping with hydrogen and this one's overlapping with hydrogen.
So me looking at this, I'm saying that's separate people. Would that be correct or no?
Well, what we find is that when carbon bonds with hydrogen, it actually bonds with 4 hydrogens, and it does make a tetrahedron.
Okay.
Remember, the p orbitals are at 90-degree angles to each other. They're perpendicular, like the x, y, and z axes, or coordinates. And so, just like the H2S, this predicts that this bond angle would be 90 degrees, and that you would have a molecule that is CH2. CH2 doesn't exist. CH4 does, but it has a bond angle of 109.5. So something's missing. We can't just overlap these standard atomic orbitals. So why do atoms in a molecule have to be the same as atoms in a molecule? Why do orbitals in a molecule have to be the same as those in an atom? They don't. So we're going to look at hybridized orbitals. So this is a mathematical procedure. So you're taking these two orbitals and you're like averaging them together, sort of. Very complicated math that we're not going to go into. These things are still localized on atoms, but they're going to have different shapes and energies than before. So the hybrid orbitals will minimize the energy of a molecule because they maximize the overlap that you can get. You've got bigger overlap because the electron probability density is more in one direction than equal on both sides. It does require energy to hybridize these orbitals, and so it only happens when there's a payback of energy by a bond forming. So we're just going to look at hybridization of interior atoms and assume that the outer terminal atoms are unhybridized.
Is it kind of like a catalyst in a way?
No, not like a catalyst. But I can relate this to the quantum hotel. We're going to remodel the rooms. So some general statements. The number of standard orbitals added together always equals the number of hybrid orbitals. So you could say orbitals are conserved. In hybridization, you can't make extra orbitals or lose orbitals. The particular combinations that get added together are going to determine the shape, right? And the particular hybridization is the one that gives the lowest energy. So those calculations are very messy, and we don't want to do them. So we're just going to use VSEPR theory and electron geometries to predict the hybridization. Okay, let's get to the good stuff here. If we look at these 4 atomic orbitals on carbon, so these are the valence electrons, there's a 2s orbital, and there are 3 2p orbitals. And so what we're doing here is we're going to say, instead of having a 2s room and a 2p room, let's just draw that. So here's this is the second floor of the hotel. And so that's a bed. And this is a bed, and this is a bed, and this is a bed. So here's the P room. It has 3 beds. It can hold 6 electrons, right? And here's the S room. It can hold 2. So this is the S room and the P room on the second floor of the Quantum Hotel. Okay. What we're going to do here, we've got a group of electrons. They all want to be in the same room together. So we're going to remodel the floor for them. Oops. So we're going to take out this wall. Oops, that's not what I wanted. Okay, can't do that. I'll erase it then. So we're going to take out that wall. And now all 4 beds are in the same room. Well, we can't call that an S room or a P room anymore, right? So we're going to call this an SP3 room, because it has 1 bed from the S room and 3 beds from the P room. And we can't charge less for this bed than we do for those beds, because they're all in the same room. And how do you really establish who's sleeping in which bed to charge them differently? You can't. So we take these 4 different beds, these 4 different orbitals, and we hybridize them so now they're in the same room. All the beds are the same energy. They all cost the same amount. So these are degenerate orbitals. And we had 4 electrons here. 2 were sharing a bed in the S room because that was cheaper. But now if they're all the same price, those guys aren't going to share. They're going to each take their own bed. And now we have 4 half-filled orbitals. So we've got 1 electron there, and 1 here, and 1 here, and 1 here. Okay?
So why not call it SP4, like SP3?
We call it SP3 because we took 3 p orbitals and 1 s orbital.
Oh, okay.
So yeah, there's 1 s and 1, 2, 3 p orbitals. So SP3. 1 s and 3 p's makes 4. Well, what would this look like for these weird balloon shapes, right? Well, here you've got an s orbital, and here are those p orbitals, and you throw those into the computer and you mash it around, and this is what you get. So these are now 4 orbitals that are equally spaced, oriented in space, a tetrahedron. They have 1 end, 1 lobe that's really much bigger and 1 that's smaller. So remember, this was like a standing wave that the electron was, and so the electron is in both sides at the same time. Right? It's not going back and forth. It's a standing wave. It is on both sides at the same time. Very mind-bending. So now we've got a standing wave where one end is really small and 1 end is really big. And if we tried to show these little stubby ends when we put all of them together, it would get like even more confusing. So we're just going to ignore those little guys. And we're going to take these, now they look more like turkey drumsticks. We're going to take these guys and show them all together, and they're going to look like that. Now we have 4 hybrid orbitals, and they're going to spread out in 3 dimensions and make a tetrahedron. Okay? So the hybrid orbital diagram would have all 4 of those orbitals together. It's 1 room in the quantum hotel. They are equal in energy, and so Hund's rule applies, and we're going to fill these with 1 electron first and then pair them up if we need to. These are going to look like the purple ones here. I love this because blue and red makes purple. right? And so we had the blue orbitals and the red orbitals, and when you mix them all together, you get hybrid orbitals, which are purple. So here I have 4 half-filled orbitals. Each of these can overlap with the half-filled orbital on a hydrogen. So now the carbon is going to bond to 4 hydrogens. And what's the angle? 109.5, which matches experimental observations. So this agrees with experimental observations, whereas overlapping the unhybridized orbitals did not agree. Questions? Mm-hmm.
Are these the only ones that are going to have hybridization, or is this going to happen for the other?
There's more than this one combination. Yeah. That's why I want to just get any questions out of the way right now before we get into more. Hybrid orbitals can accommodate a lone pair. So if we look at nitrogen, nitrogen's atomic orbitals, we got S and P, and we had 1, 2, 3, 4, 5. Oops, 5. When those hybridize, they're going to be 4 of them all at the same energy level now, an sp3. And then we're going to stick those 5 electrons back in. 1, 2, 3, 4, and the 5th one's going to pair up. So if we look at this, we see there are 3 half-filled orbitals. And so those can pair up with a half-filled s orbital from hydrogen. So this can bond with one hydrogen, this one can bond with another hydrogen, that one can bond with another hydrogen. This guy is already full. So here we have our sp3 hybrid orbitals, the balloon tetrahedron, right? This one has a lone pair in it. This one is half-filled. It overlaps with the blue s orbital from hydrogen. And this one overlaps, and that one overlaps. And so we end up with this trigonal pyramid molecular geometry. The bond angle is 107, which is less. It's getting a little closer to the unhybridized p orbital, because with this lone pair, the hybridization is not complete. But that's a little detail we're not going to worry about. Any questions? So the idea here is that you've got these balloon orbitals, and if you have one electron in an orbital from one atom and one electron in an orbital from another atom, they can overlap. Those electrons will spin pair, and that's our bond. Okay? How many sp3 hybrid orbitals result from the hybridization of 1s and 3p orbitals? It's not a trick question. So on the second floor of the hotel, here's the S room and the P room. This is 1 bed and 1, 2, 3 beds. If I hybridize these, if I put them all together, I break down the wall that's separating them. How many hybrid orbitals do I get? How many beds are there in this new room? 4. An S and 3 P beds, right?
Oh, that's it?
That's it.
Oh.
Yeah, this is not a trick question.
Then why they made it so complicated before?
Well, I don't know.
Woman, that madness before was just like, bro, what? I literally said I haven't seen an example. I understand how to do
Every
this.
time you say P-bed, I really think P-bed.
Oh, God.
You know, my children are finally past that, but we have a puppy. And he just like peed in my bed the other night. And you have to wash everything. And then like a couple days later, he gets like this red, I left a sparkling ice on the bed, and he bit it open and it was red and it just like soaked through. I'm like, you have to wash everything again.
It's a good thing you have your own laundromat in your house.
Yeah, and it's a good thing he's so cute. That's what I said about my children. It's a good thing they're so cute, or they wouldn't be around anymore. I should probably delete that from the recording. Okay. So let's look at a different combination. So here, if we take an S and two of the P's and combine those, we're going to get 3 sp2 hybrid orbitals, and we're going to have one unhybridized p orbital that's left. Let's see. Oops. If I can. I'm still kind of working on how to draw this. Okay, so what we want this time is we want to include this bed and those two beds. So let's see if I can do this. Yes. We're remodeling the hotel. We're moving the wall. That's too much? So there was a wall here, and we're going to take it down. And we're going to build it over there. And we're not too worried about why. We just can't go too far here. So this has an S and 2 P's in it. And there's one bed still left in that P room, right? Nothing happened to it. So these are going to be degenerate. They're going to have the same energy. Oh, there's another train. This is kind of fun. Thursday during class, I think there was one.
What?
I know, right? No distractions. Okay? So, we're going to take an s orbital and 2 of the p orbitals and hybridize those, mash them together. So now we're going to get 3 equivalent orbitals, and they're going to be oriented in space equally, spread out as much as possible, like the balloons, right? So again, we're ignoring the little stumpy ends. We put these together, and we're going to get a trigonal planar structure, right? And then where is the unhybridized orbital? Well, it's sticking up, sticking straight out from here and going straight back. Because these two are perpendicular in the x and y, and so the z one is left, and so it'd be sticking straight up and down. So H2CO has sp2 hybrid orbitals. So here's carbon. It's got 4 valence electrons, right? So if we hybridize these, we take these 2 and combine it with that, we're going to get those sp2, and then we've got the unhybridized p orbital. So when we put these electrons in, 1, 2, 3, the difference in price, the difference in energy between these has gotten much smaller. And so we can put an electron by himself up here instead of having him pair up here and leave that one empty. So here's the hydrogen. We've got an orbital half filled. So that can overlap with one of these, and another hydrogen can overlap here, And then we've got oxygen, and the oxygen is got two half-filled orbitals, and these two can overlap as well. You thought the other balloons were crazy.
I think a bone.
I think these look like fun pool toys. So here's the trigonal planar sp2 hybrid orbitals. So we made 3 orbitals that are identical. So that's like 3 balloons. They're going to make a triangle here. And they each have 1 electron in them. So one of them is going to overlap with the hydrogen, and another one's going to overlap with this hydrogen, and the third one is going to overlap with one of the p orbitals of the oxygen. And then we have this half-filled unhybridized p orbital, and we have an unhybridized orbital from oxygen that's also half full, and those are going to overlap, but they kind of have a hard time doing it because they're parallel to each other. So these guys are overlapping end to end, and these guys, well, you know, round is just round, but it's overlapping with one end of this orbital. And here we have these 2 orbitals that are parallel, and they're kind of like reaching towards each other. They're bending over.
They look forced.
Hmm?
They look forced.
So reaching. We're gonna reach our legs over too. These bonds where you're overlapping with the end of a hybridized orbital, these are called sigma bonds, and this is called a pi bond. So if you tip your head to the left, it's kind of like a pi symbol, right? Greek letter pi. The letter sigma, these are sigma or bonds. The letter sigma is like a circle with a little tail on it, right? If you look from oxygen to carbon along the length of this, it's going to look like a sphere, right? You got 2 balloons just overlapping with each other. It's going to look round from the end. This is not going to look round from the end no matter how you look at it. So when we have 2 p orbitals side by side and they overlap, they form a pi bond. This looks like 2 bonds, but it is 1 bond. Because this was 1 orbital, it was just a standing wave, right? And the electron was on both sides at the same time. So this is just like a really funky standing wave. But this pair of electrons is on both sides at the same time, because electrons are weird that way. Here, if we have a p orbital overlapping end to end with another p orbital, this forms a sigma bond. On the end, it looks like a tube. Right?
So you said that one's a bond as well?
This is a sigma bond because it's end to end. And the pi bond is always between unhybridized p orbitals. It's always going to be 2 p orbitals make a pi bond. Okay? So back to that picture. Here's our hybrid orbitals, right? And they are overlapping end to end with other orbitals. And this is an unhybridized p orbital. That's why it's red. And this is another unhybridized p orbital, and those are overlapping side to side. So we can call this bond pi colon CP-OP. What we're doing here is we're saying, well, what elements are involved in this bond, and what orbitals are they using? In a pi bond, it's always going to be just p orbitals. So this is 1 bond, and it's indicated like this. this bond is an overlap between carbon and oxygen. Carbon is using an sp2 hybrid orbital. Oxygen is using a plain old p orbital. So this is sigma c sp2 dash o p.
So it's safe to say that the sigma will always be S2P?
The sigma bonds is where the hybrid orbitals are going to be.
Okay.
Yeah.
Oh, so whatever, it could be the SP3 or.
Yeah, you can have sp3, sp2, sp. The pi bonds are always going to be p orbitals. No hybrid orbitals in there. And then we can describe these bonds between carbon and hydrogen. Again, it's a sigma bond. The carbon is using an sp2 hybrid orbital, and the hydrogen is using an s orbital. So we get more insight with valence bond theory than the Lewis model. What we see is that that double bond between carbon and oxygen actually involves two different kind of bonds. And so whenever we look at a Lewis model and we see a double bond, that always is going to correspond to one sigma bond and one pi bond in valence bond theory. Those pi bonds are generally weaker because they don't overlap as well. It's kind of literally a stretch for them to overlap. The end-to-end overlap of the sigma bond is better, and so the sigma bonds are stronger. So if we're going to break one of those bonds, the pi bond is going to break first because it's not as strong. So if we're looking at a molecule that has a single bond, so here I've made that model. So here we have carbons, and each carbon has 2 hydrogens and 1 chlorine. In the model and in real life, there can be rotation around the single bond because it's an end-to-end overlap, right? And they can spin relative to each other. When we have that side-to-side overlap with the one in the middle, then you've got like this, or I don't know, it's kind of messy. We'll just do 2. And now you can't spin anymore without breaking one of them, right? So in the model, when we have a double bond, let's see, gunk on it. So over here, where we've got this double bond, the rotation is restricted. I can't rotate. It works in the model too. I can't rotate it anymore. So a compound like this actually has 2 different forms. Because in one form, the chlorines are on the same side of the double bond, and in the other form, like this one, they're on opposite sides. So valence bond theory explains that. Lewis theory does not. And here again, looking at space-filling models. So we get rotation around the single bond. We do not get any rotation around the double bond. And so there's 2 different forms of these molecules. Pass. Okay, sp hybridization. Okay, so here's our s and p orbitals, and this time we're just going to hybridize 2 of them. So here's our s. There's a p. So this time we want to take the s in just one of those. So we can do that. Now we're going to call that SP because it's an S and a P. Right? So we have 2 rooms here, 2 beds in this room, and the energy is between the 2 original rooms. And then we've got the unhybridized p orbitals We've got those beds that are just in what's left of the p room, okay? So when we hybridize an S with one P, we end up with two drumsticks in opposite directions. So two identical orbitals, just oriented differently, and just like the balloons, they're going to take as much space as they can, and so they'll be on opposite sides. It'll be linear. And then we've got two unhybridized p orbitals that are just in there as well. So if we look at the Lewis structure for acetylene, which is, really disturbingly like the formula they showed us. Like, why do we have to draw that? Anyway, we see that this carbon has two groups, and that carbon has two groups. And so we'd say, well, this is going to be a linear molecule. Here's our hydrogen, here's a carbon, and we can hybridize, we can make two hybrid orbitals. And really what we're going to be doing is we're going to be looking at, well, how many electron groups are there? That's how many orbitals we need to hybridize. So here we need to hybridize two because there's two groups. So we take an S and a P. So we're going to get S and P, and then we've got these two two p orbitals that are unhybridized that are left over. And so each carbon, again, can form 4 bonds. You thought the other one was bad. This is a triple bond. So here are sp hybrid orbitals in opposite directions. One of them is overlapping end to end with the hydrogen. The other is overlapping end to end with a hybrid orbital from the other carbon. So that's a sigma bond, CSP, CSP. And these on the ends are sigma, CSP, HS. And then we have this Z orbital, and I guess that's the Y orbital, the up and down one. And so they're going to reach across and form pi bonds. So here we have 2 pi bonds and 1 sigma bond. Like really weird balloon art, right? It does kind of look like a hot dog. What's the hybridization of carbon in carbon dioxide? We need the Lewis structure to answer that. How many electron groups do we have? How many electron groups are on the carbon?
4.
There's 4 bonds. How many electron groups? 2. So I need 1, 2 groups. So I'm going to have sp hybridization. What if I need 4 groups? 1, 2, 3, 4, sp3 hybridization. What if I need 3 groups? 1, 2, 3, an S and 2 P's. So we're going to use Vesper theory to tell us what the hybridization is so that we can avoid yucky math. Okay? So we're going to look at the central atom. The number of groups is the number of beds we need to pull together in that hybridized room.
Oh, so SP2.
sp2.
Okay.
Wait, for this one?
Yeah.
2 groups.
Oh, 3.
sp.
2. Oh, 2.
Right?
Oh, I'm sorry.
Yeah. It's a little confusing because P2, there's the 2, right? But the plus the S is 3. Yeah, so this one's going to be sp. Pardon me? Yes. So this is saying that I took 2 beds from the P room. and one from the S room, right? And these are all together. So I have 3, right? And so then those would be my 3 electron groups, and those are the hybridized orbitals. So if we look at this guy, right? This carbon has 2 groups, 2 electron groups. So we want sp hybridization. We're going to make 2 identical hybrid orbitals. One's going to go this way and one's going to go that way. They're going to make the same geometry that we saw in Vesper. 2 groups, linear, right? So those are linear. Well, those p orbitals are still there, right? And one of them goes up and down, and one of them goes in and out. Train. It's the p orbitals that'll make the pi bonds. These hybrid orbitals can't make pi bonds because they're only on one side, right? But these are on both sides, and so they lean over towards each other to make the pi bond. And so we have one happening above and below, and we have one happening in front and behind. It's kind of crazy, huh? Yeah. So we talked about expanded. No, I think that's the same one. We talked about expanded octets. So in valence bond theory, what happens here is now the hybridization is extending into the d orbitals. So on the 3rd floor of the hotel, there's a P room. And the D room. For valence electrons, the valence electrons are going to show up in S and P because the next electrons after those get filled would go up to the next floor and be in the S room. So what we're going to see is that these d orbitals are just sitting there. But do hotel rooms that don't have people staying in them disappear, or do they still exist? They still exist, right? So there's nobody staying here, but they are there. This is why only 3rd period and greater can expand their octets, because we don't have this on the 2nd level. There's nothing to expand into. So what we can do here is we can take and do 5, right? So there's 4. Whoops. Maybe we should do it like this. Give each of these a label. So I've got, what we did is we're just like moving the wall over, right? We're remodeling the floor. So now I've got a bed from the S room, I have 3 beds from the P room, and a bed from the D room. So instead of calling that SPPPD, like SCCCD, we're going to call that SP3D. So that's if you have 5 things. What if you need 6? You take another D. And so then this becomes D2. Okay? So if we go 5 things together, the 5 groups, we've got the S and 3 P's and a D. We get 5 identical orbitals. What do 5 balloons do? They make this trigonal bipyramid. Now, each of these might be half-filled, and they can overlap with other half-filled orbitals. There are also these unhybridized d orbitals that are just sitting there. So here we have arsenic pentafluoride. So the arsenic is going to do this sp3d hybridization. So essentially we've got this trigonal bipyramid, and then each of these is half-filled, and so it can overlap with a p orbital from a fluorine. We can bring in one more, so we have 6 beds all together, and that's going to make this octahedron. So the 6 balloons, right? So here we have 6 hybrid orbitals, all the same energy. And now there's 3 unhybridized d orbitals that are left. And we're not going to see anything happen with those, but they're still there. So here's sulfur hexafluoride. We look at this and we say, well, we've got 6 electron groups, right? So 6 electron groups. I start running out of fingers, so that's kind of hard. So 1, 2, 3, 4, 5, 6. sp3d2, right? 6, they're going to arrange themselves like 6 balloons would do. They're going to make that octahedron. Each of those can overlap with a half-filled orbital from fluorine. And the geometry matches up with what we learned about from VSEPR theory. So how do we know which hybridization scheme is best? Well, the rigorous method is you look at the degree and type of hybridization, and you calculate it to give the molecule that has the lowest overall energy. Boring. We're going to go with good enough for Chem 1A. We're going to assign hybridization scheme from the electron geometry of the interior atom. So we're looking at number of electron groups. So what if we have 3 groups? S, P, P, sp2. We've got 5 groups. 1, 2, 3, 4, 5. sp3d. And you know, if you want to come in to the exam and write things on your fingers, that's fine. This is not 100% accurate, but it's good enough for Chem 1A. And we're in Chem 1A, so we're going to be happy with that. So this is showing the number of electron groups, the names of those geometries, and the hybridization scheme.
How do you say the last one?
Pardon me?
How do you say the last one?
Hybridization scheme?
No, the last one.
Octahedral? Octahedral. Linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. And then those other ones are going to come about if we have some of these with lone pairs in them.